Hello everybody, welcome to this video. In this video, we're going to begin talk about section 3C. All right, so section 3C is about matrices. Hopefully that is a topic everyone have already seen in your earlier linear algebra class, right? So, but for the reason to make the content complete and self-contained, we're still going to define what is an m by n matrix. We're still going to introduce the operations like the addition, scalar multiplication, or multiplication among the matrices are in this section. But I think a relatively new thing here, or maybe at least the less familiar thing here, is to explain the connection between our matrices and the linear maps we have been talking about in the last two sections in section in chapter 3. So there is a very close, strong connection between the matrices and the linear map from a finite dimensional vector space to another finite dimensional vector space. All right, so then toward that end, so that's why we begin this section at least to make the definitions and then also mention the connection in terms of definitions between the matrices and the linear maps at this point. All right, so let's get started. I will go ahead and share the notes here. All right, so I already just wrote the title here, but we're going to write down more things. All right, so this is the section 3C, matrices. So let's first define the matrices, and then we're going to talk about why we would like to know this from a perspective of the vector spaces. All right, so then the definition here should be very familiar for everyone. All right, so we're going to let the m and n use these two small letters, and each of them is a positive integer. All right, so an m by n matrix is a rectangular array with m rows and n columns that looks like the following matrix notation here. So we can either draw a big pair of brackets, or the book sometimes still use parentheses. It does not matter to me, or just one of this. And then, by the way, I think this definition like is 330 here in the book, or we may refer to this number. So then we put it A11, and then of course the next one is A12 and A13. The last one in the first row is A1n. All right, so then the first subscript of each element, each entry, is to tell you the position of the rows of that entry. And then since there are m rows, so the last one begins from, well, the last row begins with the am1, am2, and then up to am comma n. All right, so this is m rows, n columns is m by n matrix. All right, so for example, if we have something like a 2, 5, 3, -1, 7, 0, right, we know this is a 2 by 3 matrix. So if we ask you find the A, let's say 2, 1, then that is the second row, the first entry. This is -1. If you find something like A, 1, 2, then that's the first row, second column, so that's 5. All right. So then using these two subscripts associated with each entry, we can identify the location, and then we can identify what that number is. All right. So this is the, I think for almost everyone, this should be a quick review of what a matrix is. All right. So now why we care about the matrices, right? Of course, the matrices, there are different ways to introduce where they come from. In our linear algebra class, when you set up a system of linear equations, right, you can see, well, if we have something like x plus y equal to 5, x minus 2y equal to 0, then we know the x, y are just the names of the variables, and then what really matters are those numbers, the coefficients in front of x, y, and the numbers on the other side of the equations, right? So you could either write a coefficient matrix or augmented matrix, including the numbers on the right-hand side of equations, but that's one way to introduce where the matrices come from. All right. So for us, in this section, we're going to explain this in a different way. We're saying is if you have a linear map T from a finite dimensional vector space V to a finite dimensional vector space W, all right. So let's suppose, all right, so V and W, these are finite dimensional vector spaces. And let's assume the T is a linear map from the V to W. Then one thing we can say about this T is if we know any finite dimensional vector space has a basis, right? So if V has a basis and then W has a basis, then how this T is working between the V and the W can be completely described or determined by how T acting on those basis vectors in V. All right, so then let's make a more mathematical way to explain this. So let's also suppose this list V1 up to Vn, right? So this is a basis of V, and then let's say W1 up to Wm, right? This is a basis of W, right? Then this T, what do we mean the T can be just uniquely determined by the action on those V vectors? That means on those vectors in the basis of V, right? So that means if you know what the TV sub 1 is in terms of those W vectors in the basis of W, if you know what the T of V sub 2 is in terms of W1 up to Wm, and then you know every T of V sub j up to the V sub n, if you know how each this T of V sub j can be represented by W1 up to Wm, then that's all we need to know, right? Because all other V vectors can be written as a linear combination of the basis vectors in V, V1 up to Vn. And then since the T is linear, so then by the linearity, then we know that can be the T of V can be written as a linear combination of T of V1, T of V2, up to T of V sub n. Well, if you know all those T of Vj has something related to the W vectors, then that means every T of V can be expressed as a linear combination of those W vectors. And then so knowing how the T acting on the basis vectors or the spanning vectors here in the V, then that's going to help us to know exactly how the T works on any vectors in the V space. All right. So in other words, what we want to say here is if we have the T sub k, a V sub k is for any k here, this is equal to something as a linear combination of those W vectors. All right, and then, well, how many T of V sub k we have? Well, k is from 1 to n, right? So in other words, if you list this individually, maybe, that's what we can do next, or to kind of actually list this individually, at least for the first few, then there should be n equations here because the V sub T of V sub 1, T of V sub 2, and so on, right? The n equations, and then among those n equations, and each one on the right-hand side, how many terms of this in that sum? Well, there should be m terms, right? Because W sub 1, W sub 2 up to W sub m. So we need the coefficients in front of all those W vectors. So the way we do this is we're saying, well, let's associate the second coordinate with the k, and then let the first one change. So this will be a 1k and then A2K, and then up to AW, MK, or AMK, match this. So then how many A's here in each one of those equations? Well, there are A1K, A2K up to AMK, so there are MA's here. Right? So and that's for every K, right? So in other words, if you write this out with we pick up the K from 1 to 2 and so on. So what you can see here is TV1 is A11 times W1 plus A21 times W2 and up to AM1 times W sub M, and the T of V sub 2 is this is 2 here, so this actually should be A12 W1 and then A22 W2 and then up to AM, 2 WM. Okay, and then we keep going, and then the last one is T V sub N here. That is A1N W1 A2 N W2 and then AM, N WM. All right. So then there are in this case M equations are, and then on the right hand side for the W, there are N equations on the right hand side for the W vectors. There are M vectors in the basis of W here. All right. So this one, if you write this A together in a matrix, right? So we hopefully still make it consistent as M by N matrix. So in other words, these coefficients in front of each equation here, or along each equation, is not the entries along the row of your M by N matrix. They should be the entries along the column. All right, for instance, the A11, A21 up to AM1, those numbers in the first equation there, these are the entries in the columns of that matrix A. So this matrix A will be A11, A21 up to AM1, right? And then A12, A22, or notice we write each column here, and AM2, and then this keep going. At the end is A1N or A2N, and then up to AMN. So this is still a M by N matrix, right? But it's very important. I think sometimes the notation here and how they associate with the basis vectors is a little bit challenging here. Right? But remember, the one way to remember this, we're going to actually write down later. Right? You can put the V on the top of the even above your matrices, and put the W on the other side, and then that we can help you remember this. But right now, let's first introduce this definition here. So this A, or the A itself, is not a good notation because there's no indication what this connection between this A and your linear vector T and your basis, the V basis or the W basis here. So we're going to put it together for a definition, and then we introduce notation to help everyone remember that, and then we're going to go over some examples to understand the definition here. So that's the next few things. So let's first introduce the notation here. So let's summarize what we said. So those scalars, or sometimes we call the entries A, J, K, completely determine the linear map T. The linear map T, because a linear map is determined by its value or by its values on a basis. All right. So we talked about this before, but we're going to go over another example, specific example to explain this statement here. All right. So then this matrix, the M by N matrix, all right, this one formed by all those A's. This is called the matrix T. We probably call this matrix T here. Well, no, let's put the A here, but let's call this a matrix of T. Okay, it's a matrix of T with respect to the basis. Well, we have two bases here, right? One is the basis in the vector space V, and this other the basis in the vector space W here, right? And we introduce the notation, so we denote this matrix by this notation. So we put a capital M here, well, of course means the matrix, and then we put the T, so what is the linear operator, a linear map we talk about, and then we specify what are those two bases. Because obviously if you change the basis, this matrix most likely going to change. All right? So it's important to either you specify what the T and what the two bases are, or if it's pretty clear according to the context, most of the time that means you are using the standard basis, right? For instance, in Fn, you're going to use like 1, 0, 0, 0, 1, 0, and so on, right? If you're using the standard basis, then you probably, if there's no ambiguous, according to the context, then we can ignore the writings of the basis of V and the W. All right? So you just write M of T, but otherwise you also specify what the two bases are. All right. So a way to remember this matrix is to place the V on the top above everything, right? You can see, well, I have V1, V2, and then up to Vn here, and then place the W along the side, or you already put on the left-hand side, maybe W1, W2, up to Wm here, right? So that way, once you write this, or if you remember, like V is on the top, right? Because, well, anyway, this is from the T is from the vector space V to the vector space W, right? So the first one, maybe you want to, the way I remember this, the first one you want to place it higher. You want to write down the basis of the first one first, right? That makes sense. So you're going to place this, this V vectors along a row, and then you're going to play down wrote down the vectors of the basis vectors of W along the side, right? So once you finish this, you can already see, well, there must be M rows, because the W1, W2 up to Wm, right? So there must be M rows, and then if you look at this vertically, well, V1, V2 up to Vn, so there are N columns. It's pretty clear. In this case, you're talking about M by N matrix. Right. So for instance, if you're doing something from R3 to R5, right? So then in R3, there are 3 vectors in the basis of R3, right? So that means you have 3 columns. And R5, well, there are 5 vectors in the basis of R5. So then if you place those W1 up to W5, then there are 5 rows. So if there's a linear map from R3 to R5, then that can be characterized by this 5 by 3 matrix, right? And then you just put the A and then take the position, like if this is 1 and then this is 1, so A1, 1, and then this is 1, this 2, A1, 2, and then up to A1N. Right? And the second row here is A2, 1, A2, 2, up to A2N. All right. And then the last one is AM1, AM2, up to AMN. Okay, so that I think will be a nice way to help you remember where this matrix come from and which number goes to which. All right, so in terms of the order of the dimensions, that matters, right? 3 by 5 and 5 by 3 is different, right? So which will be the right case? And then once we have this one definition introduced, all right, let's go back to first say why are this linear map can be uniquely determined by the t on the vector on the basis vectors in the V there, right? So let's consider, for example, let's consider a very basic one which does not make a lot of calculation for us. So let's consider a t. Why this thing jumps? Let's consider our t, which is a linear map from, let's say, from R2 to R3, right, where we know this t of 1, 0 is equal to, let's say, 1, 2, 3, and the t of the other 1, 0, 1 is equal to 4, 5, 6. Okay, so then we do not actually define a t by a general formula. We just say, well, let's say this t is linear from R2 to R3. It's linear because that L R2 to R3 is linear, right? And then we're saying, well, let's know the information, how the t acting on a basis. This is the standard basis of R2, right? We know the t of 1, 0 is 1, 2, 3, 0, 1 is 4, 5, 6. So are those information enough to help us figure out how this linear map t acting on any vector in R2, right? So then if you have any xy, right, so this is a general assumption in R2, right? So then what's going to happen? Well, the idea is then you can write this xy as the linear combination of your bases. All right, so no matter what your bases are, you'll always be able to represent that uniquely into a linear combination of these basis vectors. All right, in the case we use the standard basis, that's the easiest thing to do. It's just x times 1, 0 plus y times 0, 1. Then the t acting on this is the same as the t, apply t on this linear combination. And well, since the t is linear, so this is x t of 1, 0 plus y t of 0, 1. And well, we are given information about what the t of 1, 0 is. This is 1, 2, 3. We're given information of what this t of 0, 1 is. This is 4, 5, 6. So then clearly you know what the resulting vector is, right? For instance, if they ask you find the t of 3, 5, then you just have 3 times the first vector 1, 2, 3 plus 5 times the second vector 4, 5, 6, then combine them, that's it. That tells you what is the t of 3, 5. So if you have any t of xy, you can use this way to determine what that t is. So then that gives you a well-defined linear map for any vector in R2, take any vector in R2 to any to a vector in R3, right? And then this one, if you are, let me go one more step, or we're not there yet, but if you are, hopefully everyone is, right? You remember two linear algebra, you remember how we multiply the two matrices, or how do we multiply a matrix times a vector, then it's pretty clearly, this is 1, 2, 3, 4, 5, 6, then this one times the xy, right? And then that tells you, well, for each this linear map, right, from the finite dimensional space to another finite dimensional space, we actually can represent that as a matrix multiplication. All right. So if you don't recall the matrix multiplication yet, nothing to worry about, or we're going to introduce this, include that in this section. All right. But right now, so we can hopefully, by this example, very basic one, convince everyone, yes, all right, so if we want to study a linear map over a finite dimensional vector space to another finite dimensional vector space, then all we need to know is how this t works on each of these vectors in the basis. And then, of course, for our definition there, we can say, by our definition, So this MT, and then of this two over these two bases, right? 1 0 0 1, 0 1 0, and 0 0 1, right? Over these two bases, this is also this matrix 1 2 3 4 5 6. All right, 4 5 6, and we will well, let's keep this here. All right, so we will do at least two more examples to more carefully to explain where that matrix come from. All right, where this how do you find this M? Strictly follow our definition here. Here, actually, I think I'm kind of jumped a little bit to, we already say this matrix. I just claimed this to be the matrix M associated with this linear map T here, right? But really, what we need to do is we need to actually let this xy to be 1 0, and then express that resulting vector as a combination of the bases in R3, and then we look at the T of 0 1. That resulting vector we expressed in the basis of R3, and then give you this matrix. All right, so there are a little bit of detail missed here, but let's look at the next one, which is a very similar question. We're going to more carefully explain where the M from. All right, the purpose, mainly for the first example, the purpose is to show you, so the matrix, well, not the matrix, but the linear map is determined by how the T acting on the basis. So let's look at another example. It's from the book. This one says if T is from F2 to F3, or it could be R2 to R3 or C2 to C3, is defined by T of xy, or anything in F2 is x plus 3y, 2x plus 5y, and 7x plus 9y. Okay. Then the question is, let's find the MT. Okay. If we do not specify the basis, so then we just take this for as a convention, like then we mean the standard basis. All right. So the basis, so the standard basis for F2, this is 1 0 and 0 1. Or sometimes the books just write like kind of like a row vector. I sometimes write as a column vector. It does not matter. Right? And then the standard basis for F3, then this is 1 0 0 0 1 0 and 0 0 1. All right, so either way is fine. Actually, to me, I think the vertical ones are easier to see, but let's stay with the book. All right, so we have this. So how do you find that matrix, right? So here is nothing directly given. Of course, you can still try to, if you already know the matrix multiplication, you can go ahead to write this into a matrix times xy. That could be one way. But that right now, let's strictly follow our definition to think about this. Remember all those A values, those scalars, how we construct them, where they come from. Well, if you look at our definition here, those A values, you let the v1, v2 up to vn to be your vectors in your basis, and then you find what each of this tv1, tv2, each of them what is, and then you express them into a linear combination of the vectors in W, and then those weights, those scalars, form the matrix A. All right, so that's how we do that. And remember, in each equation, your A values will make a column in your matrix. So we will follow that idea, all right, to follow the definition of where that M of T come from. We're going to use that to work on this example and write the matrix. All right. So then the first thing is you ask yourself, what is T of 1 0? All right, T of V1. Well, P of 1, 0 is x is 1, y is 0, so this is 1. And x is 1 times 2 is 2, plus 0 is 2. X is 1, y is 0, so 7 plus 0 is 7. So I have this one. Right? And then do not stop there, right? So what we need is to write this resulting vector as a linear combination of the basis vectors in F3. And it's pretty clear this need to be 1, and then the second component need to be 2 here. The third weight here need to be 7. All right, so that is a 1, 2, 7. And then let's look at the t of 0, 1. So this is the second vector in the basis of F2. You only have 2, all right? And then x is 0, y is 3, so 3. X is 0 times 2 is 0, plus 5 times 1 is 5. And then quickly the third one is 9. So this is 3 times 1, 0, 0, plus 5 times 0, 1, 0, plus 9 times 0, 0, 1. 0, 1. Now, so we're doing pretty good up to this point. So the last thing is just to write this MT. All right. So remember, there need to be 3 rows, 2 columns. Because if you place the vectors of the first vector space on the top, that only V1 and V2, 1, 0, 0, 1, right? If you place the vectors from the basis of W along the side, then there is 1, 0, 0, that's first one, 0, 1, 0, second one, 0, 0, 1, the third one. So there are 3 rows. So this is a 3 by 2 matrix. And then those numbers 1 to 7 form the first column, all right, not the first row. And the 3, 5, 9 gives us the second row here. So this is a 3 by 2 matrix. So this is the matrix comes from the linear map T under the standard basis from F2 to F3. All right, so that's how we find this one. Strictly follow the definition. I hope this example give you more details on how we find this matrix using the definition. So this is using a F2 to F3. Let's add another one. So this next one will be an example using the polynomials. Or I think in the first edition it did not include this example. I think it's nice to also actually add one, not just using the F and Fm there, but using a polynomial case for us to better understand this. So the next one, I think the example 3.34. So the next one, 3.34 there. So this, let me write this down. Okay. So 3.34 example here. All right, another one. This one says well, something wrong with the computer here. Okay. So example here, right? So this one, we define the differential operator. All right, this is, of course, the linear. I can check that. So let's consider this. Take the polynomials degree less than or equal to 3 to the polynomials degree less than or equal to 2. All right. So the same question is, let's find this matrix associated with this differential operator, and then from the vector space. Well, so what is the, let's say the standard basis here, right? So what should be included in the basis of P3 and P2 there? For P3, we need 1, we need a constant, we need x, we need x squared, and we need x cubed. And then for P2, we need 1, we need linear term x, and we need x squared. Of course, this is not the unique choice, but this is probably the easiest choice. All right, so let's stay with this. And then, in order to find this one, what we need is, okay, hopefully that's gone. So what we need is follow the idea before. Right? You want to ask yourself how this differential operator is acting on each of these vectors in the basis of P sub 3 of R. So that's what we need to figure out. And then since we're taking the derivative, so very quickly, by the very basic calculus 1 knowledge, we know this derivative of each. And then once you know the derivative, then the next thing is, can you represent each function as a linear combination using the basis in the other vector space? What is the other vector space? The basis is 1 is x squared. Well, in order to make a 0, obviously you need a 0, and you need a 0, and you need a 0. And then the second one for 1, well, we need a 1 times 1, 0 times x, and then 0 times x squared. And this one, we need a 0 times 1, 2 times x, and 0 times x squared. To write a 3x squared as a linear combination, we have 0 times 1, 0 times x, and 3 times x squared. All right. So once you have this, you know this m of d. All right. I will, well, probably still write the basis anyway. So then you know this one here. All right. The book very quickly give you the answer, but we're trying to add some explanation here, right? So you know those numbers, and those numbers along each equation, these numbers goes vertically, all right, not horizontally, vertically. So you have 0, 0, 0, 1, 0, 0, 0, 2, 0, and 0, 0, 3. So this is a 3 by 4 matrix because you're mapping something from dimensional 4 to dimensional 3. So then it's a 3 by 4 matrix. All right. So hopefully seeing this, I will understand how we form the matrix, where that come from. All right. So this is a very tight connection between your definition of your linear map basis, and then make the connection. Basically, it's like a one-to-one correspondence, right? To give you what this matrix looks like. All right. So that's a definition. And the last part in the first recording is, let's just quickly recall the two operations defined on the matrices are addition and scalar multiplication. I'm sure everyone knows that. And then let's prove actually the matrix of the sum of the maps is the same as the sum of the matrices of the maps, and a similar property hold for the scalar multiplication. All right. So let's define. All right. So of course, if we add two matrices together, they must be the same dimension. All right. Otherwise, it's not going to work. So if you have one m by n matrix plus another m by n matrix, then you just add the corresponding entries together. Bm1 to Bmn. All right. So then this is just equal to, you have A11 plus B11, and so on, A1n plus B1n, AM1 plus BM1, AMn plus BMn, right? So you have this, and then let's make an example. If you have something like a 1, 2, 3, 4, 5, 6, plus something like maybe 0, or negative 1, or 4, and maybe a negative 3, or 7, 10, something like this, then we just have 1 plus 0 is 1, 2 minus 1, 2 plus negative 1 is 2 minus 1 is 1, and you get a 7, here's 1, here's 12, here's 16. All right, so I'm sure this one everyone already very, very familiar with that. So we add the two matrices together, and then the other define the scalar times the matrix. Right? So if there is a lambda, some kind of a lambda times m by n matrix, all right, times any matrix, then this will be just distribute the lambda to each term in this matrix, right? So it's not only multiplied on one of them, but it's multiplied on every single of them. All right. So for example, right, if we have 5 times this 1, 2, 3, 4, 5, 6, then this is 5, 10, 15, 20, 25, and 30. All right. So scalar multiplication. Now, of course, you may think, well, I also have the, we also can do the multiplication, right, among two matrices if their dimensions match. Well, that's something actually we're going to talk in the next recording. All right. But right now, let's say why we care about this. Well, because we can add the matrices together, right? But you can also add the two linear maps together if they both from the V to the same W, same way to the same W here, right? And then of course you can also have a linear map. You can multiply by a scalar A from F, or have A times T. That's well-defined operation. Then what is the relation between the new map and then the new matrix? Right, or the old map and the old matrix. So then these are the two propositions. I think one is a 336, the other is a 329. All right. So this one, each one give us the confidence saying, well, that is nice because we don't have to every time worry about how to use the definition to write down the new matrices. All right. So then the first one, when the T and the S are two linear maps from the same V to the same W, we're saying you can add these two linear maps together. The sum is a new map, and then the matrix of this new map. All right. So naturally, we would like to this happen. It happened is, well, this is just the matrix of T plus the matrix of S. A very natural way. So you don't have to do the calculation anymore, right? If you know what the matrix T is, what the matrix S is, just add together because it's much easier to just add two matrices. All right, that's a very straightforward calculation. Instead of you write down the TS, you go over the basis again and do the representations, no necessary. All right, so you just add it together. And of course, the second one, I should make the C a little smaller, like a scalar. So the second one says if you have a scalar times T, then the matrix associated with this new map is the same as the scalar C times the matrix of T. All right. So this is whenever C is in F and T is a linear map from the V to W. All right. So I think let's try to prove one of them, or maybe just prove the 336 and leave 339 to you as an exercise, or none of them is too difficult. I probably explain one and then help you get started. So you should try the other one. All right. So let's do the proof of 336. All right. So, well, we needed to have some kind of a basis here, right? So let's suppose, or the notations here, let's suppose the T from the V to the W and the M associated with the T is A11 or to A1N, AM1 to AMN. So what this tells us, right? So this tells us where this come from, or this tells us for every Vj in your basis, or any, wait, let me see. We use a V sub K here, right? Because that's the original one. I mean, notation is fine, but the K is probably better. So this is, well, the A1K times W1, all right? And then A2K, W2, and up to the A, so this is from N to M. So this is going to be A1K, the K's column, right? A1K, A2K, and then this is the AMK, AMK times WM. All right, because their basis is V1 up to Vn. We're trying to be consistent before, right? So this is the basis, and then the other basis is W1 up to Wm. Okay, so we're good, right? So this is how we, by the definition, this is how we formed this matrix M of T there, right? And then similarly, if you assume the S is from the V to W, then there is a matrix associated with S. So this is B11 up to B1n and BM1 up to BMN. Okay. BM1 up to BMN. Right, so then this means if you have S acting on the NAV sub K here, this is B1K W1 add up to BMK WM. All right. Now, what is the sum? Well, remember the sum of this acting on any vector V by our definition is the T acting on the V plus the S acting on the V. So this is our definition how we add two linear maps together, right? So then this is equal to, well, you just take the A1K together, W1 here, right? And then AMK WM here, and then plus the B1K W1 and the BMK WM, right? And then, of course, we can associate, we have the associative property in the vector spaces, so you can factor out W1 and add the B1K and the A1K and the B1K together, and then up to the last term, there, every column there's a common factor W some J here, right? So what this tells us? Well, then by the definition, right? So that's how we form the matrix, right? What we mean the matrix of T plus S? We said that means you take those scalars in front of all those linear representations and then form them like each equation is a column, each equation is a column. So then it's pretty clearly if you let k equal to 1, let k equal to 2, up to k equal to n, then your matrices will be, the entries will be just like this. And then keep going, and the last one, AMN plus BMN, AM1. This is the, this is A, actually, sorry. This is the A1N plus B1N, and then up to the AMN plus BMN, right? And then, well, by the definition, so this is by the definition of M, we have this, actually probably put it here, right? And then this is the same as A11 up to A1N, AM1 up to AMN plus B. And this is based on our definition of how we add the two matrices together, right? So this is the better definition of matrix addition. And so that, but this one is M of T, and this one is M of S. All right? So then that proved, right? So when you add the matrices, it's corresponding to you add the linear maps. So when you add the linear maps, it's corresponding to you add the matrices. All right. So then the proof of the other one of the 339. All right. Let's leave this as an exercise. I encourage everyone to go over this process to understand how that works. All right. The scalar times T is the same as the scalar times the M of T. All right. This is kind of one-to-one correspondence. All right, so to summarize, in this first recording of this section 3C, we recorded the definition of matrices, we record definition of two operations of matrices, but more importantly, we said, well, if we have a linear map, how do we correspond that to a matrix? And the operations between the linear maps can be also characterized equivalently by the operations of the matrices. All right. Of course, another linear map is the multiplication, or the in old terminology, composition of linear maps. So can that give us something? And the answer is yes. All right, so we're going to see that in the next recording. All right, see you there.